now we want to do an example where we find the relative maximum and relative minimum. Any relative maximum, relative minimum, there might be more of one of each. There might be none of each, or none of one, whatever. Okay, so let's let our function be f of xy equals xi plus y squared j, and let's let our g of x function be related to x, or let's let our constraint be x squared plus y squared equals 4. Okay, so we're looking for the maximum of f of xy equals xi plus y squared j, subject to the constraint g of xy equals 0, where g of xy is x squared plus y squared minus 4. Now why do we put the minus 4 here? Well, we want our g of x to equal 0. If x squared plus y squared minus 4 equals 0, that's the same as saying x squared plus y squared equals 4. And actually we want something to be equal to 0 here, so we just bring everything onto the left-hand side and we have our constraint function. Constraint function equal to 0. Okay. Well, the gradient of f and gradient of g are very straightforward. I'm not even going to read them to you. Calculate them in your head. You can calculate them very easily. Now, we have the condition that del f equals lambda del g. Okay, and I'm not going to write down these two equations here. I'm just going to write down del f equals lambda del g, because that's equivalent to writing down these two equations. Okay, well, of course, you can write down these two equations, but you should see that all this means is that whatever the I component is of your g has to equal lambda times the I component. Well, I'm sorry, whatever your lambda component, let me say it right, whatever your I component of f is, del f is, you multiply it by, it's equal to lambda times the I component of del g. In other words, the components of del f have to all be lambda times the components of del g, meaning the same can be said for the j components. And this simply means that the I component here, which is 1, is lambda times the I component here, which is 2x. So you get 1 equals, and I'll just write it as 2 lambda x. That's lambda times 2x. Okay, and then here, the j component of del f has to equal lambda times the j component of del g. And that tells me what? That tells me that 2y equals 2 lambda y, or lambda times 2y if you wish. Okay, well, taking these two conditions, which are exactly what you get if you wrote these equations down without thinking about what they mean. From this equation, lambda has to equal 1. Okay? Then, if lambda equals 1, well, we plug that into this equation. And what do we get? We get 1 equals 2 times 1 times x. So, x has to be negative 1/2. I'm sorry, it's not negative 1/2, it's 1/2. Be careful. Okay, so we have the point 1/2, 1. What are we going to do with that? Now, let me back up and say that a lot of times you also have to go to your constraint function to find values of x and y. In this case, our value of lambda came out very easily. Usually you would have to solve these two equations and get x in terms of lambda or y in terms of lambda, and then plug that in to your g constraint function. You'll see plenty of examples that do that. Just trying to give you an overview of the process though. So sometimes it's a little more complicated. Sometimes you have to solve for x, y, and lambda. Now what we get here, of course, we have to find values of y. Okay, well, the value of y is unrestricted. Okay, so we are going to have to go to the g of xy function. Which kind of contradicts what I said a minute ago. Okay, we've got to find the value of y. So what do we have? We have, first of all, our constraint function, g of xy equals 0, which tells us that x squared plus y squared minus 4 equals 0. X squared plus y squared equals 4. If we take our value of y in here, then what do we get out of it? We get x squared, we take our value of x and we plug it into here. Our value of x is 1/2. So we get 1/2 squared plus y squared equals 4. So that y equals what? Well, first of all, y squared equals 4 minus 1/4. So that y squared is, well, 3 3/4, and that's 15/4. So that y is plus or minus the square root of 15 over 2. Our potential critical points, therefore, are, let's use a different color here. Now these are critical points for the value of f as we move along the curve g equals 0. The critical points are what? X has to be 1/2. Y could be plus square root of 15/2. Or negative square root of 15/2. Okay, now I wrote a couple of things up here because when I did this earlier, I wrote something down carelessly, as happens way too often. But what we need to do now is we need to determine what the values of f are at these points. We still don't know which point, if either, is a relative max, which, if either, is a relative min. Well, our function f of xy evaluated at the first point, 1/2 square root of 15/2 is equal to what? You know, I wrote something up here that was really incorrect, and hopefully it's been bothering you. I'm going to fix this. I was thinking gradient. And I did the same thing down here. We don't have an I and a J on our function f. And the thing that caused me to realize